Imagine building computer software like constructing a massive factory. If you design it as a single continuous machine, every part depends on every other part. When one gear slips, the entire assembly line screeches to a halt. You have to take the whole system offline just to fix a single bolt. The alternative is breaking that giant machine down into isolated, self-contained workstations. Instead of one tangled mess, we get a clean hierarchy where distinct parts handle specific jobs. In software design, this is called functional independence. It's the engineering rule that says every component in your system should focus on doing exactly one thing well, without relying heavily on everything around it. We measure this independence with two specific metrics. The first is cohesion, which means internal single-mindedness. A cohesive module doesn't multitask. The second is coupling, how connected a module is to the outside world. We want low coupling, meaning the module communicates as little as possible with other parts of the system. By prioritizing high cohesion and low coupling, you isolate failures. If a bug appears in a specific feature, you can swap out that specific module without triggering a cascading collapse across your entire codebase. Let's apply this to a real problem: building software for a commercial print shop. The customer needs a system that can read job data, calculate the cost of a print run, build a work order, and send that order to the production floor. We start with first-level factoring. Here, we establish top-down control. We're not making a chronological timeline of what happens first. We're building a management hierarchy. A top-level main controller manages 3 distinct subsystems: reading data, developing the cost, and building the work order. Next comes second-level factoring, where we break those broad systems down into highly cohesive subtasks. Develop job cost is too vague on its own, so we assign it 3 subordinate workers: 1 to compute page cost, 1 for paper cost, and 1 for production cost. These workers do the math and pass the data back up. Notice the clear division of labor here. The modules at the top and middle are managers. Their only job is to direct traffic and make decisions. The modules at the very bottom are the execution workers. They crunch the numbers and format the data. When you strictly separate control logic from execution logic, you prevent processing bottlenecks. The top-level system doesn't get bogged down doing basic math. It just manages the flow of the application. Let's test this architecture. Look at the compute paper cost module. It does exactly one well-defined task, high cohesion, and it only communicates with its direct supervisor. Low coupling. It is perfectly independent. Now it's your turn. The client just added 2 new requirements: check the job's priority and pass the job to the production floor. Pause the video and decide where these 2 modules belong in our hierarchy. Did you figure it out? These are execution tasks that belong under a new management branch. We add a send job to production module to the main controller and place the 2 new execution tasks directly underneath it. This tree structure works well for a small print shop, but as a system grows to include dozens or hundreds of modules, keeping track of individual boxes becomes an organizational liability. To manage that scale, we use packaging principles, specifically the Common Closure Principle, or CCP. The rule here is simple: classes or modules that change together belong together. By grouping these 3 cost calculation modules into one package, we acknowledge that a change in pricing policy will likely affect all of them at once. Packaging insulates the system. If the client updates their wholesale paper discount, you only have to open, edit, and retest the cost package. The rest of the application remains untouched and stable. Here is the architectural blueprint for the print shop: a stable network handing tasks down to focused worker modules. Remember, this is a structural map. Left to right flowcharts show when things happen. Top-down structure charts show who is responsible. Getting that responsibility right comes down to 3 rules. 1. Structure your code so control sits at the top and execution at the bottom. 2. Enforce modularity by maximizing cohesion and minimizing coupling. And 3. Organize your modules by packaging items that change together. Mastering these principles moves you past writing code that just barely works. It gives you the tools to take a chaotic list of client demands and engineer them into a clean, resilient software architecture.